he wasn't. So I'm going to begin because someone's got to introduce Bruno and Pontecorvo, and this is where he starts. I assume that this has been talked about by this time, so these are sort of extra slides I put in. But Bruno, in 1946, has suggested, there it is, the first practical method for detecting neutrinos. And it's worth a few words. Use an inverse beta decay, whose product is a radioactive inert gas. That's the very first thing. The second thing is that the subsequent beta decay gives a unique sign of the neutrino. That is, it gives you the sign of this whole reaction. So you start with chlorine. That's an easy thing to get. You get cleaning fluid, carbon tetrachloride. That's mainly chlorine 37. A neutrino comes along, and if you're lucky, you make argon, which is an inert gas. You have an electron, which you don't care about. The argon, which lives about a month, decays to chlorine. And when it does so by electron capture. So now you have a vacancy in the K shell that's filled by a 3 kilovolt Bohr jump from the L to the K, and that's the signal. A very practical scheme. The first scheme ever invented, as far as I know, for really finding. Oh, this is a note about my sources. I used the original papers, review articles, Nobel lectures, but I used extensively the discovery stories by C.S. Wu, Richard Garwin, Valentin Telekti. I use these stories that appeared in the Adventures in Experimental Physics. That was a short-lived publication created by and edited by Bogdan MacLeish. It's, I think there were only about 4 additions to that. But it was a wonderful journal while it lasted. Yeah. Whoops. Gotta have it a lapel. At least 2 neutrinos. Okay. Davis reported his tentative conclusion that the Pontecorvo, he's the one who starts it. He comes to Brookhaven Labs. He doesn't know what he's going to be doing. He reads the Pontecorvo's classified notes from Chalk River, a paper by, when he's at Chalk River, it's a Chalk River paper about that method of finding a neutrino. He decides that, gee, that's a nice thing to do to begin with. He starts. In 1955, he reported his tentative conclusion that the Pontecorvo method did not detect neutrinos from reactors. By 1958, he concluded that the neutrinos from reactors are not detected by the Pontecorvo method. There are 2 kinds of neutrinos. A neutrino is not its own antiparticle. Also, you think so? Okay. If this is.
And you can read the.
Oh, I see. Oh, I didn't know that. Okay. Anyway.
So yeah, stay here and you can read the.
Yeah. Can you hear me okay now? Oh, good. Okay. Willie Tanowski and Jack Steinberger do the experiments which absolutely pin down the fact that the pi minus is negative parity and the pi zero is negative parity. I'm not going to go through the reactions that they use. It wasn't so much that the reactions are so so much, because people had sort of deduced the negative parity using these reactions before, but this was Willie's PhD thesis, and he really, with Steinberger, he measures everything in the final state. So there's no question about what the two neutrons are doing going back to back 180 degrees. So he really concludes without any question that these are negative parity states. So let's go on. In the years that are preceding 1955, lots of things are going on in high-energy nuclear physics. In particular, the cosmic ray groups are finding all these kaons in their photographic plates, the stacks of emotions, and then accelerators are coming on board that can reach the energies that you can get find these kaons. And so the kaons become a zoo of particles, as Oppenheimer called them. At the yearly conference in Rochester on high-energy nuclear physics, this becomes a real topic of conversation. How do you understand these kaons? In the 6th volume of that in 1956, that whole problem comes to a head. All the well-known theorists are there, some experimentalists, and the C.N. Yang reported that it gives a summary of things. There are 5 different types of K-mesons. The 5 types of K-mesons all have about the same mass, about half that of a nucleon. All have about the same lifetimes, around 10 to the minus 10 seconds. It seems very likely that there's essentially the same mass, that they're essentially the same lifetime. And he says, each with almost, one tries to discover, he says to this group of 100 and some odd people in that meeting, to discover whether we are dealing with 5, 4, 3, 2, or 1 kind of K-meson. And the tau theta puzzle becomes the real focus of all of their discussions. The K mu 3 and the K pi true have got common names of tau and theta. The tau decays to 3 pions. Its parity must be negative times negative times negative must be negative. The theta decays to 2 pions. Its parity must be negative times negative positive. No one proposed a solution to this problem. There was one remark by Feynman. The first one, Yang stated before that it may perhaps be best to keep an open mind on these matters. And Feynman voices the following question posed to him by Bloch, Marty Bloch. Could it be that if theta and tau are different particles, if parity, what if parity is not I can't read I can't do 2 things like this. The parity states to the same particle. That is parity conserved in k decay? And what I wanted to really point out is how Feynman put it. Feynman asked, does nature, he has spoken for Bloch. Bloch doesn't want to talk himself. He's embarrassed. He gives a question to Bloch. He says, does nature have a unique way of defining right-handed and left-handedness, or left-handedness? And Yang replied, we have looked into this matter without arriving at a definite conclusion. Well, T.D. Lee and C.N. Yang are really working full-time on this. And they've come to the conclusion that you must do experiments to determine whether or not parity is violated. That whether or not the tau and theta are in fact the same part. I should just mention in passing that there were, quote, solutions to this problem other than the parity one. No one believed them, including the people who suggested them. But they did. One of them was T.D. Lee, that it would be two particles, one with a very, very short lifetime and the other with a 10-second lifetime. Anyway, they suggested in their paper, the paper that won them the Nobel Prize, they suggested a relatively simple test of the angular distribution of the beta electrons from the spin-oriented nuclei. And for the meson decay, measure the angular distribution of the electrons with respect to the direction of the muons that are emitted from stop pions. No one at the time was rushing to test meson decay. Wu, C.S. Wu, Chen Shen Wu, was already working full-time on testing beta decay. She's another Columbia professor, and we'll be talking about, here is C.N. Yang, here is T. Lee, and here is a picture of Wu from about that time. I liked the picture that I had that was much younger. She was a good-looking woman. And smiling. I like that. Anyway, in that discovery story, she tells how T.D. Lee came into her little office in the early spring. That's before the Rochester conference. T.D. questioned her about the status of the experimental knowledge of beta decay. He told her about the tau theta puzzle, how it led to their questioning parity conservation. And he really makes it very tough for her to say no, because he knows C.S. Wu pretty well. If the answer was to parity violation, that should be observed in the beta asymmetry from polarized beta decay nuclei. Well, she is listening to this thing. She knows just how difficult this is. But that in itself is a challenge she liked. She has to learn how to put a detector into a tube that's sitting down here at near 0 degrees K. And she has to figure out how she can put a source down in there that's polarized. So Wu, by this time in her life, is really considered the person who is doing experimental studies of beta decay. She has solved most of the most serious questions having to do with forbidden decays. And this is the challenge of a lifetime. She persuades her husband, Lu Guan, to take the trip to China alone that they were going to take, and she buries herself in a full time. And for her, that means at least 16 hours a day, at least 7 days a week. If there were more, she'd spend them. And she starts in May, full-time on this thing, and finally in December, she's keeping Lee and Yang informed of this, but then she reports her results, physical review letters. First of all, there's a question of the polarization, which, I should just mention that a graduate student of hers learned how to grow the crystals. No one, and Wu has been told, you're going to have an expert in this thing, and it'll take them 6 months or a year to figure out how to make the crystals that you want big enough that it'll allow you to polarize the cobalt-60 source that she uses. Well, first of all, she uses the gamma rays. She has a gamma ray detector here, another one the other direction. She uses that to tell her that she's actually polarized the cobalt-60. The cobalt-60 is a 5+ decay, a 4+, so it's a loud gamma teledecay, and it leads to first a 4 to 2 transition of and then a 2 to 0. It's 101.37 MeV or 1.17 MeV, and the anisotropy of that tells you whether you've got it polarized. Here, oops, I got to go backwards. One is right on top of the other. The top, yeah, I know it's, but I'm pressing this. I'm this way with the computer too. This is the polarization. You see the polarization starts, but then it gets weaker and weaker and weaker. And this is pure asymmetry. It starts and gets weaker and weaker and weaker. It matches it directly. It's essentially 100% polarized. And that she communicates on Christmas Eve, I think. I was told that by a colleague. Anyway, Leon Letterman regrets. Well, Wu tells her colleagues at a Friday luncheon, remember that it's a Friday luncheon, about her results. Letterman goes home that evening, and he begins to ponder what her results means. He has thought about this. He's read the paper of Lee and Yang, and he made an estimate. This is too difficult. The effect is going to be too small. Now he thinks again on this thing and says, the effect is going to be large. He says in his book on the God particle, he says, the lost fame, the lost fortune. And that evening, he calls Richard Darwin. If anyone has been reading biographies of scientists recently, the biographer of him starts off with a title genius, and then goes on. Probably the most influential physicist, influential in the government that we've had. But Richard is outstanding experimentalist. He calls him, he's not at Columbia, he's working at IBM, but he's spending all his time at Columbia apparently at that time. Calls him and tells him of Wu's results. And then he explains, Letterman explains to him how simple the experiment is going to be. We can make the pions, they'll make the muons will decay, and we just put our detector, and according to a parity violation. They'll just decay in the forward direction or in the direction of the muon. We'll just we've got a detector sitting there. We'll just take that detector, measure the count rates, move the detector. It's a bit of a job, but we'll move it, and we'll get an answer. Darwin arrives. They arrive at the Nevis synchrotron, and Darwin says, no, that's the wrong way. Keep the detector fixed. Let's put a magnetic field on it. And I've calculated that it'll only take about 50 Gauss to really rotate that over the 2 microsecond decay time of the muon. And we'll just watch it sweep by. Well, that's a much better idea. They then kludge together that experiment, and they do the first run that Friday evening. Well, the results are erratic, but encouraging. They've seen some very positive results, even though they don't last, they can't reproduce them and anything else. The machine shuts down for the weekend. That allows Dick and the others to go in, make better equipment. He's pretty good with lathes and such things, and he's a superb electronics guy. The next Monday, they start again. By this time, this is what the equipment looks like. Here, you can see it, as I can point to it. The beam is coming down from the top. The carbon piece that Dick says that he machined himself, a plug that stops the muon without it depolarizing very much. It comes down, and it's going to be detecting it in the detector. They put a magnetic field around, a couple of Helmholtz coils around it to get the magnetic field. And as a function of the strength of the magnetic field, and they look at the count rate, and look what it looks like. It's a 22 sigma effect. And that was done in 3 days. Wu took 8 months. No, 7 months, I guess. First, that's a whole puzzle for historians. Why does someone not do something when it could be very simple? And leaves it up to someone else who doggedly solves all the problems that she has to solve and make it happen. So now parity is violated. It's violated 100%. I'm going to then later talk about Leon's measurement of the the parity has been violated in both beta decay and muon decay, and we now turn to the Goldhaber, Grodzins, and Sanyar experiment, in which we measure the helicity of the neutrino. Now, if you want to measure the helicity, you've got to transfer that helicity of the neutrino to a particle. Oh my goodness, I got a hustle. You've got to measure to one which is measurable. And I do want to go to the next. So let's go on. Telegin gets very fascinated by this experiment. So he writes down in a paper written several years later of 10 different separate attributes that such a decay scheme should have, if you want to transfer that. And very quickly, you want a K decay, so the final state is two-body. You want to go directly to an eigenstate that decays directly to ground, because that's the one that you're going to excite the neutrino's energy must be at least equal to the energy of the gamma ray. The state must decay before the recoil nucleus declines. So we're going to take a K capture. The neutrino goes up. Let's see what I have in the next line. Takes the left-hand view. The neutrino goes up. The recoil goes down. The recoil is radioactive. It's going to decay with the emission of a gamma ray. Those gamma rays which are going in a forward direction get a boost from the Doppler shift, enough to make this gamma ray have enough energy to excite the same state in stable samarium. That will last for a time which is short, 10 to the minus 14 seconds, and you'll catch it in here. I did that experiment without anybody else involved. I did it on a tabletop. That's the tabletop. This is me at that time. This is the experiment. The samarium is in cardboard. The sodium iodide detector is down here. The magnet is Goldhaber's idea. He's changed a simple experiment which says, wow, I've detected the neutrino's momentum better than anyone else ever have, and I was just excited about that. He changed it into an absolutely classic experiment. You've got to give me, I got to have time to. So here is the experiment again. The middle graph shows the signature standing out above the background when I put gadolinium in the cardboard case that you put together with duct tape, and here is the results showing the negative helicity of the neutrino. Let's go on. That's Goldhaber. Okay, so Wu or TD has been talking at Columbia to a group of people at a Friday luncheon, whatever it was, about experiments that you could do at high energy with a neutrino beam. And in the audience is Mel Schwartz. And Mel is a fellow, so he's not on the faculty. I don't think he's a graduate student at that time. And he comes up with the idea that evening. And the idea is very simple. Whoops. This is the drawing that he has in the physical review letters. Namely, you make a beam, you start off with a beam of protons, make pions. The pions decay mainly forward into muons. The muons will decay from parity, it'll be going forward, and you'll get muons plus a neutrino. And that will go to, two neutrinos, I'm sorry. So all you do is you protect your detector from all of the charged particles, and the only thing that you're going to see is a neutrino beam. And this is Jack Steinberger, who joins them with a couple of other people. These are the spectra that you should see of neutrinos, and they analyze this. This is, I should mention that I'm about 1 minute away. They build this detector. That's 13 meters of steel that's in front of that's 13 meters of steel protecting this detector. That's the neutrino detector. So the beam has come down here. You give it enough time for the decay to happen. This is the detector. Each of these spark chambers weighs a ton. So there are some 10 tons of spark chambers. And what do they get? They get 34 single muons out of 3 times 10 to the 16th circulating protons in the accelerator. They see no electrons at all. Only muons are observed. Only electrons are observed. Only mu. I'll get it straight. Only the mu's are observed. Bottom line, the neutrinos are different for the 2 decays of electron decay and muon decay. I'll stop there. I think we've finished. Thank you.
I have in fact 2 questions. The first is, why did Madame Wu not get the Nobel Prize?
Why did what?
Why did Madame Wu not get the Nobel Prize?
I think because she's a woman. If you want to know my personal view. I mean, the Nobel Prize has a history of not giving to women who deserve it. And of all, I mean, it was given, there was room for a third person. Who else was to get it? It wouldn't be any of the Steinberger and Leon group. I played around with things that summer. You don't count the experiments that's not published. No, that was just a.
Sorry, may I just add that, I mean, these things are, I mean, they're confidential for 50 years. That's the lower limit. And what happens that both Professor Lee, who's born 1926, and Professor Yang, who's born 1922, are still alive. And thus one cannot say why. I know it, but I won't tell you. Because I was a member of the Nobel Committee for 12 years. So I looked into it. I was exactly as curious as you are, Dieter.
Okay. So my other question is, how independent is the proposal for a high-energy neutrino beam from Mel Schwartz and from CERN? I mean, you know that Steinberger was one of the 3 who wrote the proposal to the first neutrino beam at CERN before he went up when it turned out.
You know, it was on a slide. I didn't talk about it, but the neutrino beam was suggested a year before any of the Columbia group got involved by Pontecorvo.
Okay.
Yes, and that, and he did 2 things in that. First of all, he had almost the same idea of doing it. He estimates the count rate 1 an hour. That's exactly what the Columbia group has estimated was 1 an hour. He says that we don't really think that there's any. He said, I don't believe that it can be done with present accelerators. They thought that it couldn't. The Columbia group thought it couldn't be done with present accelerators, but that pessimism turned to optimism when they found out, learned about the spark chambers. Because the whole problem of all the neutrino experiments have is finding the ways to discriminate against the background. And that means either you don't have a background or you can measure it so objectively that you can say, yes, that's background. No, that's not background, that's real. The spark chamber gave them that possibility. And they realized, it had been developed at Princeton, they realized that if they used that, they had a chance of finding it, even though there were so few events that would really qualify, that they could get rid of all the others. And if you read their paper, it's all about how they, not about how you make the beam. It's how you analyze the data to make sure there are no electrons in that.
But well, that is only half the story. At CERN, they had the bubble chambers. In fact, 2 bubble chambers.
Yes, and the bubble chamber is the other way of doing this, of course. The giant bubble chambers. But I think, as far as I know, the CERN experiment that goes is after this one. No one else has ever disputed the fact that the neutrino beam was actually put in practice first by the Columbia group.
Well, I know from a remark of Gilberto Bernardini, when he was asked about who had the idea, he said, of course, Pontecorvo.
Yes, that's absolutely right. Pontecorvo and the Columbia group finds it out when they go to publish their paper, when it's in proof. That's when they're told about the Pontecorvo paper. It's in Russian. It hadn't yet reached the translation chair, and that's when he reads it. And if you read the Nobel Prize talks, then they try to give him as much credit as they dare, given the fact that they also did it independently.
However, it's also true that the complete setup was ready at CERN. It was only due to a mistake in calculating the flux.
Well, someone else will have to answer. I don't know. I wasn't involved in that at all.
How did you find the europium as a possible candidate for that experiment?
All right.
That's unique.
Yeah, that's right. Yeah, I didn't find it. It found me. All right. You're going to learn a little bit of nuclear physics. I come to Brookhaven, and I have been doing cloud chamber experiments on particles, cosmic ray particles. I come to there because my professor was a student of the right people in England. And so I'm given my very first problem by Goldhammer. And that is, we believe that all nuclei that have 88 neutrons or fewer are spherical in shape. Those that are 90 neutrons and greater are spheroidal in shape. The evidence is very slim, but real. It's atomic physics arguments. Why don't you look at europium-152, which decays by K capture and positron emission to the rotational band side and by electron decay to the vibrational side. So I'm doing those experiments. And one summer Henry Kendall comes down and works with me on it. Another Nobel Prize winner that gets involved in some way on these things. Anyway, I discover this state, there's a 1- state, and I'm curious about it. And I'm a technician, and Goldhammer is an idea person. And I say, gee, this could be part of the rotational band. If it is, that dipole is going to be very fast. Is it possible to do these experiments, an experiment to resonantly scatter that state and measure its lifetime? No idea about helicity at all. I do the entire experiment without the magnet, and I see this beautiful resonance state, and I'm ecstatic. I've written that my goodness, they paid me to do this. It was such a marvelous experience. I'll never forget it. Goldhaber comes back from a conference in Rehoboth, calls me into his office and says, we can use this to measure the helicity. And I say, yeah, let's do it. I could rush down. We already have the magnet because we've done some experiments with polarized gamma rays before. We had a magnet for that purpose. And we plunk it down on the top of and we start counting. In a few days, we have the answer. That was it. No, it was, nobody has found another decay that works with. That's why Telegny was so impressed. How could you find this thing? How could you find something in which the energy between the europium state, which is a 0 minus, and the ground state 0 minus of the samarium, is essentially split in half. Half of it is going down to give you a gamma ray, and the other half is giving you the neutrino. The neutrino has just the right momentum to give the recoiling samarium enough of a kick, to give it enough velocity, to give you a Doppler shift, which brings you within range of taking up all of the energies and momentum that you have to lose in exciting a state up and getting it de-excited on the way down. And it worked. It needn't have worked. We could have been a few electron volts off, and it wouldn't have worked. But it did work. Yeah.
Well, fascinating. So maybe we have time for another question. Oh, Cecilia.
If you look into the paper of the Brookhaven people, they had about 30% of the events in which the neutrino did not produce any muons. So were they neutral current events that they missed?
I didn't get the last sentence.
About 30% of the events did not produce muons in the final state. I mean, they have just one little paragraph about that. Were they neutral current events? So they didn't go back to check and see what they were.
I don't know. I have no idea.
No, because the other part, you have all those, neutrino plus something, things like that. Sure. I mean, there is another part. Otherwise, you don't know
they
that.
missed. They know how many neutrinos are coming from the hyperons. They know how many neutrinos are coming.
They know the target. They know that they're going to the target. I mean, you know that? You know the answer? I mean, I was just wondering.
I think the short answer is yes, that they missed that, and they had speculated that there was neutron background in the beam, and so that led them to discount this. But my understanding is that, in retrospect, that was in fact neutral currents.
Well, they spent time killing the neutrons by adding more and more shielding. That was their biggest background to begin with.
You have a very short question.
No, it was kind of a joke to Cecilia. Cecilia, so when are we going to know about the Nobel Prize missing by Madame Wu?
I hope it will take a long time because, they got the Nobel Prize in 1957. It was very, very quick because the papers on parity violation were actually published in January, 1957. And these gentlemen, they went to Stockholm in 1957, and they were invited to the king. It turned out that the king, Swedish king, was archaeologist also, and he knew a lot about Chinese literature. And Yang told me, you know what? Lee and I, we know nothing about Chinese history. We went home and started learning it. Okay. Anyway, the point here is that 57 plus 50 makes 07, right? I mean, so in principle, in 07, you could open the archives and look at it. But that is a lower limit. So you have to make sure that the people involved are all gone. So you see, so I hope Professor Yang will live longer. And Lee too.
Yeah,
Sorry?
let me make a comment there. Cian Yang, I think, will live a long time. He's got such a young child. He's got to watch it grow up. But in conversations with him, he professes to know a fair amount about Chinese literature and Chinese history. That's all I could. He does not back down to Americans about such things.
No, but he started learning, he said himself, soon as he came back from his Nobel Prize. 1957, he started, collecting stuff and being interested. So the Nobel Prize did something good to him.
Okay, so let's thank Professor Grodzins again.